When you're building any kind of reliable application, the database can sometimes feel like this chaotic place. You've got crashes, network failures, and users all trying to mess with your data at the same time. Today, we're going to demystify the one essential tool that brings order to that chaos, the database transaction. So here's what we're going to cover. First, we'll talk about why we even need transactions. Then we'll decode the famous ACID guarantees. After that, we'll dive into the dangerous race conditions that can sneak into weaker systems. And finally, we'll get to the gold standard, serializability, and how modern databases actually pull it off. All right, let's jump right in. Why do we even need to have this conversation about transactions? Well, because building systems that don't break is really, really hard. I mean, in the real world, everything is constantly trying to fail. Your app crashes in the middle of an operation, the network drops, and this is the big one, you have multiple people, multiple clients trying to change the exact same piece of data at the exact same time. This concurrency can lead to some of the most bizarre, unpredictable bugs you'll ever see. We need some way to shield our application from all this chaos. And that shield is the transaction. The easiest way to think about it is like a container for a bunch of database operations. And it gives you this very simple but incredibly powerful promise. Either every single thing inside this container succeeds or none of them do. It's a total all or nothing deal. If anything at all goes wrong, the database just hits this giant undo button, and it's like it never even happened. Now, for decades, the safety guarantees of transactions have been summed up by this one famous acronym, ACID. It's kind of the traditional set of promises that databases make to you, the developer. But here's the thing. From a senior engineering perspective, you have to know that while ACID is a fantastic mental model, in the real world, the term has been watered down so much that it's almost just a marketing buzzword. What one database calls ACID compliant can be wildly different from another. The devil, as they say, is always in the details. So let's break down those details. Atomicity is that all or nothing promise we just talked about. Durability means that once data is committed, it's safe, even if the power goes out. Isolation is the idea that concurrent transactions can't interfere with each other. Now, consistency, this one's a little different. This is actually your job as the application developer. The database gives you atomicity, isolation, and durability as the tools so that your application can make sure the data is always in a valid, consistent state according to your business rules. Now, if ACID were this perfect, unbreakable shield, our story would end here. But in the real world, there's always a trade-off between safety and performance. And most databases, right out of the box, choose performance by weakening the I in ACID, isolation. And this is where the cracks in the shield appear, and these subtle concurrency bugs, these race conditions, start to creep in. Let's start with a really common one, read skew. The simplest way to explain it is this. You see a temporary, totally nonsensical state of the world, just because you're looking at different pieces of data from slightly different moments in time. And this example just nails it. Okay, so Alice has 2 bank accounts, each with $500. Her total is $1,000. Now, a transaction starts to move $100 from account 2 over to account 1. Right in the middle of this, Alice runs a query to check her total balance. Her query reads account 1 before the money arrives, so it sees $500. Then it reads account 2 after the money has left, so it sees $400. From her perspective, it looks like she only has $900 in total. $100 just vanished into thin air. That's read skew. Okay, next up is the absolute classic, the lost update problem. This happens whenever 2 transactions do what's called a read-modify-write cycle. They both read the same value to start, they both calculate a new value, and then whoever writes the result last wins, completely wiping out the other one's work. Just look at this timeline. User 1 reads the counter value. It's 42. At almost the exact same moment, user 2 also reads the value, 42. So user 1 adds 1 and writes back 43. Then user 2, who's still working with that old value of 42, also adds 1 and writes back 43. We had 2 increment operations, but the counter only went up by 1. An entire update was just lost, gone. All right, now for the sneakiest, most devious one of them all, write skew. This is way more subtle than a lost update. Here, you have 2 transactions that read the same objects, but then they go on to update different objects. The problem is that the decision each one made was based on a premise that is no longer true, and that leads to some business rule getting violated. This on-call doctor's example makes it crystal clear. So the rule is, at least one doctor must be on call at all times. Right now, both Alice and Bob are on call. Alice starts a transaction and checks the rule. Are there 2 or more doctors on call? The database says, yep. At the same time, Bob starts his transaction and asks the exact same question. The database also tells him, yep, we're good. So Alice's transaction goes ahead and updates her record to off-call, and Bob's transaction updates his record to off-call. They both commit, and the result? 0 doctors on call. The business rule is completely violated, even though they never touch the same row.
So how in the world do we prevent all of these crazy race conditions, read skew, lost updates, and especially that tricky write skew? Well, the definitive answer, the gold standard, is the strongest possible guarantee: serializable isolation. You know, the concept behind serializability is actually beautiful in its simplicity. The database promises that even though it's running a bunch of transactions in parallel, the final outcome will be identical to some serial, one-at-a-time execution. It's like forcing everyone to get into a single file line. It's an elegant solution that just completely eliminates all possible race conditions. So if serializability is so great, why don't we just use it all the time, for everything? Well, the senior perspective is always about trade-offs. And historically, serializability came with a pretty big performance penalty. Let's look at the 3 main ways engineers have tried to implement this gold standard.
You've basically got 3 main approaches. The simplest is serial execution. You literally just process one transaction at a time. It's super fast if all your data is in memory, but your throughput is stuck on a single CPU core. Then you've got the traditional, old-school solution, 2-phase locking. This one is pessimistic. It makes writers block readers and readers block writers to prevent any issues. But this can really kill performance. And finally, you have the modern optimistic approach, serializable snapshot isolation, or SSI. This one just assumes conflicts are rare, lets everyone go ahead, and only checks for a problem right at the very end.
Now, what's really fascinating about that first method, serial execution, is how you make it work in practice. You can't have this slow, chatty, back-and-forth transaction you see on the left. All those network round trips would just destroy your throughput. Instead, you have to package up all of your logic into a single unit, a stored procedure, like you see on the right. You send the whole thing to the database, which can then execute it all in one go. Super fast, often entirely in memory. So when you're comparing the other 2 big methods, it really comes down to this philosophical difference. 2-phase locking is a pessimist. It assumes conflict is waiting around every corner, so it grabs locks on data early and makes everyone else wait in line. SSI, on the other hand, is an optimist. It bets that conflicts are pretty rare, so it lets everyone proceed and only aborts a transaction if an actual problem is detected right at commit time.
So, how does this optimistic SSI model actually work under the hood? Well, first, the transaction gets to read from a consistent snapshot of the database. It's like a frozen-in time view. Second, as it's doing its work, the database is in the background tracking all its activity. What data has this transaction read, and what has it written? Third, right before it's about to commit, the database does a final check for conflicts. It asks a critical question. Has any of the data I used to make my decisions been changed by another transaction while I was running? And finally, if the answer is yes, the transaction is aborted and it's up to the application to retry it. Okay, so we've covered a lot of ground, from the fundamental problem all the way to the most advanced solutions. So what does this all mean when you actually have to make a choice in a real-world production system? This table really puts it all together. Take a look at read committed. It's a really common default setting, but it protects you from almost none of these concurrency bugs. Now, snapshot isolation is a huge step up. It solves read skew, which is great, but look down at that bottom row. That super subtle but potentially catastrophic write skew anomaly with the doctors. Only true serializable isolation can protect you from that. The single most important takeaway here is that you must know what guarantees your chosen isolation level is actually giving you. And that leaves us with the final question, the engineer's choice. For years, the conventional wisdom was that the performance penalty of serialization was just too high for most apps. But with modern optimistic techniques like SSI, that trade-off is really starting to change. The cost of correctness is going down. So the question you have to ask for your own system is this. Is it worth paying a potentially small performance price to completely eliminate an entire class of subtle, hard-to-find, and maybe even catastrophic bugs? That's the critical decision you have to make.